Welcome back to the course of Applied Elasticity. In today's lecture, we are going to continue our discussion on the semi-infinite domain problems. In the last lecture, we were discussing about the deformation or deflection of the elastic half space when it is subjected to the normal line loading of intensity W. Now, we can consider one elastic half space or a semi infinite body which may be subjected to various types of loading. So, two such loading conditions we had considered, which are line loading. One is axial or normal line load at the tip, another is shear line load at the tip at one particular point. Now, moving further, instead of the line loading acting at a specific point O, which we are defining as tip or origin, apart from that, we may have the distributed line loading acting on the semi infinite body or elastic half space. Now, span of that distributed line loading, the distributed normal load may be finite, it may be semi infinite as well. So, if you consider the first case, the semi infinite span distributed line loading, here we are defining our tip or origin at this point O, with starting from that point on one particular side for the entire elastic half space, the load P of distributed loading, normal distributed loading with intensity P is acting, whereas for the second case, let us say this point is O, starting from that till another point O1, for this finite span the distributed normal line loading of intensity P is acting. So, the elastic half space may be subjected to distributed normal loading over semi infinite span. Starting from origin, the one entire side is subjected to distributed line loading as shown in this example, or it may be subjected to the normal distributed line loading of intensity P over a finite span from O to O1 as shown in this figure. So, in today's lecture we are going to talk about the solution of the Clement problem when it is subjected to the distributed normal loading for semi infinite span and also for finite span. So, first let us consider the elastic half space subjected to the normal distributed loading acting over semi infinite span. So, the first case. So, here the elastic half space is considered starting from the origin O, the normal distributed load of intensity P is acting. Now, here I have marked the x and y axis. So, x axis is vertically downward axis and y axis is horizontal axis, towards left it is positive. So, this entire region for which the distributed normal load is acting, that is for the negative y axis. So, for y less than 0, this distributed uniform normal loading of intensity P is acting over the half space, over the elastic half space. Now, here theta is chosen to be measured from the positive y axis in the counter clockwise direction. Hence, the range of theta is defined from 0 to pi. So, this particular positive y axis refers to theta equals to 0, negative y axis refers to theta equals to pi. Now, if I try to write the boundary condition on the surface, so here surface is no more free, some part of the surface, that is negative y axis, is subjected to compressive loading of intensity P, positive y axis half of the surface is free of any kind of normal or shear loading. So, if we are writing the boundary condition for the positive y axis, which is defined by theta equals to 0, for that, for this region sigma theta theta is 0, tau r theta or tau theta r is also 0, because no normal stress, no normal traction, no shear traction is acting on the positive y axis part, theta equals to 0. So, sigma theta theta r comma 0 is 0, tau theta r r comma 0 is also 0. Now, if you look at the negative y axis, that is theta equals to pi, the right half of the problem, for that shear traction tau theta r is 0. So, shear traction tau theta r for this region tau theta r is 0, but sigma theta theta is non-zero due to presence of this load P. So, tau theta r comma pi is 0, but sigma theta theta r comma pi is minus P. Now, why minus? Because the applied load P is compressive acting downward, and on this plane sigma theta theta direction by sign convention is upward positive. So, as the directions are different, so sigma theta theta r comma pi should be equals to minus P. Now, as if you are looking at the boundary condition, all these surface tractions are constant. They are either 0, 3 of them are 0 and 1 is non-zero, but a constant, because P is a constant. Now, if we want to have the constant stress, sigma theta theta tau theta r must be constant or function of theta. They should not be function of r. As we want to make it independent of r, stress components to be independent of r for such polar problems, for such polar coordinate problem, we can have the stress function phi to be the function or proportional to r square. So, if phi is proportional to r square, then only the sigma ij components would be independent to r. Because the order or rank of r, power of r in sigma ij is normally 2 orders lesser than the order of r in phi, by using the definition of stress components in terms of phi, the partial derivatives of phi. Thus, to ensure the constant sigma components with respect to r, they may be dependent on theta, but with there should not be any variation of sigma theta theta sigma r theta with respect to r, then only these boundary conditions can be satisfied. These can be ensured only if phi r theta is having r square terms in terms of r. No other function of radial variable r should be there in the stress function, and hence we are choosing our stress function like this, which is chosen from the general Mickel solution. So, if you look at the Mickel solution which was discussed earlier, that was having some terms which are independent of theta, then theta dependent term, then sin theta term, cosine theta term, then series with sin n theta and cosine n theta. Now, from all these terms we are choosing the terms containing r square. So, from the terms without the sine or cosine, these first term is taken a6 r square theta, then in the Mickel solution in sin theta and cosine theta coefficients no r square terms were there. So, no sin theta or no cosine theta term can be there. And considering n up to 2, we are choosing only one solution from that summation, which is sin 2 theta term multiplied with b21 times r square. Now, from cos 2 theta we can choose one more a21 r square cos 2 theta, but that term is not chosen here. If you choose that, later you can see to enforce these boundary conditions we must force that constant to 0. So, cos 2 theta term which is having r square in its coefficient, that cannot satisfy the given or present form of boundary condition and thus not included in the stress function. So, we are choosing our stress function with these two terms a6 r square theta plus b21 r square sin 2 theta. Now, moving forward with respect to this stress function, the stress component sigma r, sigma theta theta and tau r theta for the present problem can be obtained like this. Sigma r is 2 a6 theta minus 2 b21 sin 2 theta, sigma theta theta is 2 a6 theta plus 2 b21 sin 2 theta, and tau r theta is minus a6 minus 2 b21 cos 2 theta. Now, these particular stress functions and these set of stress components obtained with the help of this the definition or the relation between stress function and stress component must satisfy all 4 boundary conditions. So, if you look at the boundary condition, these were the 4 boundary conditions. So, for the positive y axis, that is theta equals to 0, we have sigma theta theta and tau r theta to be 0. For the negative y axis defined by theta equals to pi, we have sigma theta theta to be minus p and tau r theta to be 0. Now, we know that expression of sigma theta theta and tau r theta has already been derived as a function of theta and they are independent of r, which was our requirement. So, for the present form of phi, they are giving the stress field independent of r. Thus, using those for different values of theta, we can get these boundary conditions satisfied. So, let us substitute the sigma theta theta with theta equals to 0 in the first boundary condition. For theta equals to 0, this term and this term, both theta term and sin 2 theta term in sigma theta theta would go to 0 and thus the first condition is automatically satisfied. Coming to the second condition, substituting theta equals to 0 in tau r theta or tau theta r, we would be getting minus a6 minus 2b1 times cos 0, so which is equals to 1. So, this would be minus a6 minus 2b21 equals to 0 and through this we can relate a6 and b21 as a6 equals to minus 2b21. From the third boundary condition, sigma theta theta at theta equals to pi is minus p. So, substituting theta equals to pi in the sigma theta theta expression, it would be 2 a6 pi plus 2 b21 sin 2 pi, sin 2 pi being 0, this term is going to 0 because sin 2 pi is 0 and this should be equals to minus p. From that we can get a6 to be minus p by 2 pi. So, one of the constant we are able to get from this. And last boundary condition, tau theta r at theta equals to pi, that would also give us minus a6 minus 2b21 equals to 0 or a6 is equals to minus 2b21. So, you can see the second and fourth, these two boundary conditions are giving us same term. Now, substituting a6 here, we can obtain b21 as p divided by 4 pi. So, both the constants which were present in the stress function, these are the two unknown constants a6 and b21 in the stress function, we are able to obtain both of them and hence substituting those in the stress function phi r comma theta becomes this. Phi is minus p r square by 2 pi times within bracket theta minus sin 2 theta by 2. So, these stress functions is suitable for solving this problem where elastic half space is subjected to the distributed normal line loading for the semi infinite span. Now, moving to the stress components, substituting a6 and b21 in these set of stress components equations, we can get the stress fields for the present problem like this. Sigma rr would be minus p by 2 pi times 2 theta plus sin 2 theta, sigma theta theta would be p by 2 pi times minus 2 theta plus sin 2 theta and tau r theta is p by 2 pi times 1 minus cos 2 theta. So, these completes the present problem, which is the exact solution, all the boundary conditions are exactly satisfied. Now, after this elastic half space problem subjected to the distributed load over semi infinite span, let us move to the elastic half space problem subjected to the normal distributed uniform loading over a finite span. So, in this elastic half space, this normal distributed loading P is acting over a finite span from O to O1 and P is the intensity of the distributed normal loading. Now, we will try to solve this problem with the help of the Clement problem solution. What was that? Clement problem solution was like the elastic half space is subjected to a single line loading, normal line loading of intensity W at a specific point O or the tip. Now, for this we had obtained a purely radial stress distribution, sigma rr equals to minus 2 W by pi r cos theta and rest to sigma theta theta tau r theta were 0. Now, using these Clement problem solution and using the principle of superposition, we will try to obtain the solution of these problem, this one where the elastic half space is subjected to the distributed loading of intensity P. the fixed intensity, constant intensity P acting over a finite span between these 2 points O and O1. Now, considering this particular case where O is chosen to be origin. So, x axis is vertically downward from O, y axis is the horizontal axis coinciding with the free surface of the elastic half space. Theta is measured from the x axis, positive x axis in the clockwise direction positive as shown in the figure. So, range of theta is from minus pi by 2 to plus pi by 2 for the present problem, which is same as the Flement problem. Now, here this is the first case of solution. We will be solving two cases, then their superposition will give us the desired solution. So, for this first case, let us choose the stress function to be a r square theta. Why r square? If you are having stress function to be proportional to r square, then the stress components would be independent of r. That is what we want. So, for that reason we are choosing phi to be proportional to r square, and it is having only one theta dependent term, which is a r square theta. Now, with this form of phi, if we find the stress components sigma r r, sigma theta theta and tau r theta, sigma r r for this phi would be 2 a theta, sigma theta theta for this phi will be 2 a theta and tau r theta will be minus a. So, both sigma r r and sigma theta theta are equal, and that is given by 2 a theta, whereas the shear stress tau r theta is a constant which is minus of a. It is independent of r, it is independent of theta. That is what we want. Now, if we try to plot it for the free edges, so boundary condition, if you look at the boundary condition which this obtained stress field is going to result. Now, how is the boundary defined? Boundary for this problem is defined by theta equals to plus pi by 2, that is positive y axis, and theta equals to minus pi by 2, which is negative y axis. For positive y axis, theta equals to plus pi by 2. If you substitute that here in the sigma expressions, so for these boundaries on the theta plane, we have sigma theta theta as normal stress and tau theta r as the shear stress. Sigma r r does not exist on the positive or negative y axis on the theta plus minus pi by 2 planes. Only sigma theta theta normal stress and tau theta r shear stress exist on those two planes. So, for positive y axis or theta equals to plus pi by 2, sigma theta theta, substituting theta with plus pi by 2, sigma theta theta would be a pi. So, if we plot it here in the figure, we are going to have a positive sigma theta theta, positive normal stress for the positive y axis with intensity or with amplitude a pi, which is constant amplitude, and starting from this tau theta r is equals to a constant minus a. So, tau r theta is equals to minus a, and that I have drawn minus a means it is along the negative y axis, it is along the negative r direction. So, these boundary conditions at positive y axis is giving us these stress fields as shown in the figure. Now, we will go to the theta equals to minus pi by 2, that is negative y axis. So, sigma theta theta with theta equals to minus pi by 2, if you substitute here in this equation, that would be minus of a pi, and hence for the negative y part, negative y axis part, starting from point O, there will be normal stress of minus a pi acting downward, compressive distributed normal loading of intensity minus a pi is acting, tau r theta is constant, which is minus a. So, that will not be changing its sign. So, if you look at this problem, that is the first case of problem started with a choice of stress function as a r square theta. The obtained stress components are resulting a boundary condition like this, where we are having two types of forcing. The surface loading or surface traction boundary condition includes two type of forcing. The first one is uniformly distributed shear force of intensity minus a. As it is minus a, it would be acting along the negative radial direction for for theta equals to plus pi by 2 surface and positive radial direction for theta equals to minus pi by 2 surface. So, that is shown here in the figure. You can see a shear load is shown going towards the negative y axis and intensity of this shear load is minus A. This is the first surface traction present for the problem. Then the next surface traction present from the problem is the uniformly distributed normal load of constant intensity A pi, but its direction is changing its sign as you are going from plus y axis, positive y axis to negative y axis. So, towards the left of point O, we are having a tensile normal load of constant intensity A pi. Towards the negative y axis to right side of point O, we are having compressive normal load of uniformly distributed intensity A pi. Minus means it is compressive in nature. So, uniformly distributed normal load of intensity A pi is acting over the free surface, which is abruptly changing its sign at the origin. So, this gives us the complete solution of case 1 with this kind of surface boundary condition as described in the figure, with these two possible forces or tractions acting on the free surface. Now, coming to the second case, where instead of point O, we are choosing our origin to some other point O1, that is the end point of the distributed loading. Distributed loading was P of intensity P was acting over a finite span of elastic half space between O to O1. The first case of solution is taking O as origin, with that we had solved it. Now, for the second case, we are choosing our origin at some other point O1 and a stress function is chosen like this. So, phi 1, our previous stress function was phi function of r and theta. Now, we are choosing a new stress function phi 1, which is defined with respect to a new polar coordinate variables r1 and theta 1, which is having origin at point O1, and this stress function is defined as minus A r1 square theta 1. Previous stress function for case 1 phi r comma theta was A times r square theta. New stress function centered at O1 is minus A r1 square theta 1, only sign is getting changed, and with that the second case of solution can be obtained like this. So, for the first case, origin was at point O, radial variable was r, circumferential variable was theta. For the second case, origin is at O1, radial variable r1, circumferential variable theta 1. For the first case, stress function phi was A r square theta. For the second case, stress function phi 1 is minus A r1 square theta 1. Value of A is same, but variable is getting changed to r to r1, theta to theta 1, and the sign of the stress function is getting changed. As we are changing the sign of the stress function, the direction of all the free surface tractions will just be reversed. So, this second case at point O, on the point O1, which is origin, from which the positive y axis starts. So, towards the positive y axis you are having the compressive normal load of intensity A pi, and towards the negative y axis you are having the tensile normal load of intensity A pi, and for the entire surface you are having shear traction of intensity plus A. Now, if I compare these two, case 1 and case 2, and try to go for a superposition, then plus A surface traction, shear traction, and minus A shear traction will balance each other. And if you see the region beyond point O, towards left of point O, so let us divide it into 3 regions. One is this, one is this. So, this is span 1, this is span 2, and this is span 3. Here also we are having span 1, then 2, then 3. Now, in span 1, for the case 1, tensile A pi distributed load, for case 2, compressive minus a pi distributed load, they will cancel each other, the normal loading will be 0 for span 1. Similarly, for span 3, the case 1 is showing the compressive load of distributed compressive load of intensity minus a pi, case 2 is showing the distributed tensile load of intensity plus a pi, they would cancel each other. Thus, in the superimposed solution for the span 1 and span 3, there would be no normal loading. Now, in the span 2, O2 O1, both the solutions case 1 and case 2 results compressive normal loading of intensity a pi, and hence in the superimposed solution we will be having a total normal load intensity of 2 a pi between O2 O1 or span 2. So, if you pictorially represent this principle of linear superposition between this case 1 and case 2 type of loading, that would be resulting a stress distribution shown here, where between O2 O1 on this finite span a uniform normal load of intensity 2 a pi would be acting, and the region left to point O and region right to point O1 would be free of any normal load. And as for case 1 we were having a shear load of intensity minus a, and for case 2 we are having a shear load intensity of plus a, they would cancel each other. Thus, the superimposed solution is not going to have any kind of shear loading. Hence, as we have already solved case 1 and case 2 problems separately with the stress function a r square theta 1 and minus a r 1 square theta 1, with those two superimposing them, we can get the solution of this half space problem, where the distributed normal load is acting over a finite span between O to O1. Now, if I compare this P with the 2 a pi, the applied load intensity P for this problem is equals to 2 a pi, and from that we can obtain the value of a to be P by 2 pi. Thus, the stress function, two stress functions to be used, phi r theta would be P by 2 pi r theta square, which is described with respect to center O, and phi 1 would be minus P by 2 pi r 1 theta 1 square, which is described with respect to center O1. The total stress function will be superimposition or addition of these two, which will be P by 2 pi times r square theta. So, this should be r square, not r theta square. This should be r square theta minus r 1 square theta 1, and hence using these phi we can get the overall stress functions, which would be resulting a stress distribution. For that case, the elastic half space will be subjected to the distributed line loading of intensity P within this finite span O to O1, and these variables R R1, these two different radial variable, and theta theta 1, two different angular or circumferential variable, can be easily related using the geometry once the span A to O to O1 is given. This length, let us say L, this will be a given length, that is span of the external loading. For a given span of L, for any particular point, you can relate R and R1, theta and theta 1 from geometry, and thus with the help of this stress function you can get the stress components for the elastic half space problem subjected to normal loading acting over a finite span. So, in this lecture we had talked about the elastic half space problem subjected to distributed loading. We had considered two types of distributed loading, one is acting over semi infinite span, another one is acting over finite span. Thank you.